Now there are 3 main polyhedral point groups. And these are denoted T sub D, O sub H, and I sub H. And these point groups are characterized by having more than 2 high order axes of rotation, and high order means a C3 or higher. Now the point group that is denoted T sub D is the tetrahedral point group. Now a tetrahedron has 4 faces, each of which is an equilateral triangle, 4 vertices with 3 faces meeting at each vertex, and 6 edges. Now an axis that passes through any of the vertices and the center of the tetrahedron is a C3 axis, and so there are 4 of those. So we have identity, 4 C3 axes. Now we also have a C2 axis that passes through the midpoints of opposite edges. And so we have 3 C2 axes. Now each C2 axis is also an S4 axis. And so we have 3 S4 axes. And we have a dihedral plane that passes through each edge. So there are a total of 6 dihedral planes. And that is the reason for the subscript D in the notation for the tetrahedral group indicates the presence of a dihedral plane. In this case, there are 6. So the elements in the group are the operations denoted by the symmetry elements. So if we have a C3 axis, we have rotation by 120 degrees, and therefore we also have rotation by 240 degrees, which is C3 squared, and so there are 4 of those. Now in general, a power of an operation will generate a unique element if and only if the power is relatively prime, integer n, in this case 3. Now as we have an S4 axis, we also have the operation indicated by the S4, and so we also have an S4 cubed, where 3 is relatively prime to 4, and so there are 3 of those. And so we have a total of 8 C3 elements and a total of 6 S4 elements. And so the group is generally indicated this way. It is the group which has the identity operation, 8 C3 operations, 3 C2 operations, 6 S4 operations, and 6 dihedral plane operations, so that the total order of the group is 24. Now the group that is designated or denoted O sub h is the octahedral point group. Now an octahedron has 8 faces, each of which is an equilateral triangle, and 6 vertices, with 4 faces meeting at each vertex. And an octahedron has 12 edges. Now, an axis that passes through opposite vertices is a C4 axis. So we have identity and a total of 3 C4 axes. Now each C4 axis is also a C2 axis, and in addition, an axis that passes through the midpoints of opposite edges is a C2 axis. So we have a total of 9 C2 axes. Now an axis that passes through the center of opposite faces is a C3 axis. And so we have a total of 4 C3 axes. And in the case of an octahedron, the octahedron does have an inversion center, which is the center of the octahedron. So as we have a C4 operation, we have a C4 cubed operation that generates a unique element. Since C4 squared is a C2, again, the power 3 is relatively prime to 4, and so there are 3 of those. And as we have a C3 operation, we have a C3 squared operation, and there are 4 of those. So we have a total of 6 C4 operations and a total of 8 C3 operations. Now each C4 axis is also an S4 axis. So we have 3 S4 axes, and every C3 axis is also an S6 axis. So we have a total of 4 S6 axes. And we also have, once again, 6 dihedral planes. So as we have an S4 operation, we also have an S4 cubed operation, where 3 is relatively prime to 4, and there are 3 of those. And as we have an S6 operation, we also have an S6 to the 5th power operation, and there are 4 of those. And so we have a total of 6 S4 operations and 8 S6 operations. And for each C4 axis, there is a horizontal plane. And so we have a total of 3 horizontal planes. And so an octahedral point group has the following unique elements: an identity, 6 C4 axes, 9 C2 axes, 8 C3 axes, 6 S4 axes, 8 S6 axes, an inversion center, 3 horizontal mirror planes, and 6 dihedral mirror planes, so that the total order of the group is 48. Now the group that is denoted I sub h is the icosahedral point group. An icosahedron has 20 faces, each of which is an equilateral triangle, and 12 vertices, with 5 faces meeting at each vertex, and a total of 30 edges. Now, with 5 faces meeting at each vertex, an axis that passes through opposite vertices is a C5 axis, and 12 vertices divided by 2 gives us 6 of those. Now, each face is an equilateral triangle, and so an axis that passes through the centers of opposite faces is a C3 axis. And with 20 faces divided by 2, that gives us 10 of those. And an axis that passes through the midpoints of opposite edges is a C2 axis. And with 30 edges divided by 2, that gives us 15 of those. And an icosahedron does have an inversion center, which is the center of the icosahedron. So let's look at the elements. As we have a C5 operation, we also have a C5 squared, a C5 cubed, a C5 to the 4th power. Each of these powers is relatively prime to 5, so we have 6 of each of those. As we have a C3 operation, we also have a C3 squared operation, and so we have 10 of those. And so we have a total of 24 C5 elements, a total of 20 C3 elements, 15 C2 elements, and an inversion center. Now each C5 axis is also an S10 axis, and so there are 6 of those. And each C3 axis is also an S6 axis, so there are 10 of those. And there is a plane passing through and containing opposite edges, so that there are a total of 15 mirror planes. So as we have an S10 operation, we have an S10 to the power of 3. We also have an S10 to the power of 7 and an S10 to the power of 9. 3, 7, and 9 are relatively prime to 10, so there are 6 of each of those. As we have an S6 operation, we also have an X6 to the 5th power, and there are 10 of those. So we have a total of 24 S10 elements and a total of 20 S6 elements. So the icosahedral point group has the following unique elements: an identity, 24 C5 elements, 20 C3 elements, 15 C2 elements, an inversion center, 24 S10 elements, 20 S6 elements, and 15 mirror planes, so that the order of the icosahedral point group is 120. So as an example, carbon tetrafluoride belongs to the tetrahedral point group. Sulfur hexafluoride belongs to the octahedral point group. And Buckminster fullerene, or a buckyball, belongs to the icosahedral point group. Now there are 2 classes of point groups of intermediate symmetry a class that we call cyclic, and a class that we call dihedral. Now these point groups are finite point groups with order less than those of the polyhedral point groups. Now there are 4 point groups of the cyclic class. And these are denoted Cn, Cnv, Cnh, and Sn. Now, these point groups are characterized by having only one proper or improper axis of rotation, the C sub n point group has a single axis of rotation, and so the elements or the unique operations of the group are identity, Cn through Cn to the power of n minus 1, so that the order of the group is n. The C sub nv point group has a single axis of rotation, and in addition has n vertical mirror planes. So the unique operations of the group are identity, C sub n through C sub n to the power of n minus 1, and n vertical mirror planes, or reflection through vertical planes, so that the order of the CNV group is 2 times n.